Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And this is Sahil. Welcome, everybody. Mikey was not able to join us for this episode, but we have a slightly different format this time. So Tim and I will be discussing about the completeness or incompleteness of physics, depending on your perspective. And before we get started, just a few logistical things. If you're watching on YouTube, do post your comments and questions on the channel, and so we can get to them while we discuss. So Tim, I think before we start discussing, I think it's important to define for our listeners the whole point about incompleteness and why we're even asking this question to begin with.
Yeah, so I think that the reason why we're even asking this question, I mean, you might ask, why is this even a thought? Is that basically there's this mathematician, Gödel, actually, I forgot his first name, very famous mathematician. He proved something called the Incompleteness Theorem in mathematics, which basically says that it doesn't matter what kind of logical systems or axioms that you might have in any particular field of mathematics, there are always statements that may be true or may be false, but yet they cannot be proved. So this sort of tells you that to some extent that our math as a logical system is incomplete in some ways because there could be things out there that you can't even prove it. So what gives, right? And then it kind of makes you question life, like what is the broader implication of this thing?
That that sounds very depressing. Is there any like bright side to it? Just
Well, the bright
why
side
bother
is,
even doing math?
I guess at least we know, right? And I guess that it's interesting that even that statement is provable. So even that is an untrivial fact. The fact that something there exist things not provable is provable. So I don't know. Yeah.
Yeah. One of our listeners mentioned the first name is Kurt Gödel, if I pronounce that correctly. But yeah.
Yeah, Kurt
Um,
Godel. Apologies on my ignorance.
all
Should have
good, all
known. Yeah.
good. I think we got the essence of it down. I guess is there so before we delve into this, like, does this appear anywhere in the sciences? Like, it's a very sounds like a very mathy thing, but the
Yeah.
entire physics is based on math. So where would this appear?
Yeah. Well, so so I think given that physics is based on math, so in and indeed some researchers going into the more mathematical physics realm has already published papers on examples where certain physical statements may actually be incomplete. But then, of course, there's the flip side. Are these statements actually like real life scenarios? Because there's a key distinction I think we have to distinguish. There's physics in the sense of math, right? It's a self-consistent set of theorems, I guess, for the mathematically inclined. Then there's also physics as referring to the real world. Our physics, it's a way to model the real world. Whether it's actually the real world is a different story, I guess. But then this is a bit metaphysical. So I think to examine, first have to understand what does it mean really to be incomplete, to see if there are actually the real life consequences.
Yeah, I think so too. So are you saying there's something, certain problems in physics where based on the kind of mathematical framework of it, that you can't really answer it for physical systems because it's one of those theorems that you can't prove or disprove. Is that is that fair to say? Or
I would say it's more like like sure you might have theorems about physics, but the next question is like those theorems may be not provable using math. But the next question is, are those theorems actually referring to realistic system? That's the next question, right? Because I mean, this is the divide between math and science, basically, and physics in particular. physics has something more than math, that systems have to be realistic. We have to be able to run experimentation. And so, with that extra bit added on top, then the question becomes not as obvious, right? Like the logic, sure, may be incomplete, but reality, is it really?
Yeah, that is kind of interesting. I wonder, like, the evolution of physics as it starts to progress, as you'll be able to explain more and more, but you won't know more and more as a result of that. Kind of an analogy is sort of that I've heard is like we can think of an island and there's a bunch of sand that represents knowledge, and the more knowledge you add in, the more sand you put on this island, but your perimeter of ignorance grows with time. That's like probably the best
I mean, it
analogy that I've heard.
historically, I guess something like that. Maybe we sort of see trends like that, but okay, but I think in practice we really have to understand. I okay, let's just dive into like what exactly is Gödel's incompleteness theorem. I mean, for the listeners who are not familiar with it, right? And roughly, what is the logic? So, so the logic goes like this. Gödel's observation is that when we make statements about anything in mathematics, we use these symbols like, oh, something is true given something is true, blah, blah, blah. You can formalize that, but it's a list of symbols. It's just the way the human language works, I guess, to some extent. And when you do that, you can kind of enumerate every single statements and proof in math, right? And these are called Gödel numbers. So, and when you do that, you can cook up these really contrived self-referential statements. So Gödel's incompleteness theorem comes roughly when you ask the question, when you try to prove this statement, and this statement goes like this. It's like this statement is not provable. It's almost like this paradox, like, oh, this statement is false, right? Well, if it's true, then it's false. That doesn't work. If it's false, then it's true. It doesn't work. So in the same vein, this statement is not provable. Well, let's prove it. If you can prove it, then it's not provable, right? And if it's not provable, well, you just proved it. So this sort of contradiction is ultimately lies in the heart of the incompleteness theorem. It's sort of like, hey, it's not decidable, right? Basically, and then yeah. So that's the basis of it. But then, if you bring in physics, it gets tricky. So.
Yeah. I also want to take a little bit of a step back and say, would you say it's equivalent if something is like I guess incomplete? That also means it's not computable as well. Computable meaning that I can't construct an algorithm that a computer can follow in order to actually solve the problem.
Yeah, if something is not decidable, absolutely, it's not computable, basically. Well, I mean, I could be wrong. Of course, I'm not an expert in this field, but I think that's generally true. So to that end, then there is real life consequences, like you said. If something is not decidable, then it's not computable. Then if it's not computable, that means sort of in real life, we cannot decide. So actually, it's just this paper I just read briefly. So this actually happens in physics, it turns out. Okay, and these are published by some condensed matter physicists. The idea is this: if you have a bunch of atoms tiled in different ways, okay, and these atoms have electrons that move around. It's like, so imagine like a hunk of metal, some kind of crystal structure like diamonds and whatnot. You can compute the properties of these collective movements of electrons. And you can compute something called the mass gap, right? Whether these particles have a particular property, whether they kind of move. Well, yeah, let's just put it this way: whether it has this property of having a mass gap or not, right? It turns out that in math, it's been proved that there are certain questions that are undecidable, and this is the tiling problem. I think I don't understand it too well, but basically it's like if you have some random set of tiles and regular tiles, it's not clear that if you can decide whether the whole plane can be fully tiled by it or not, something like that. Okay.
Yeah, so just to translate what you're saying, it's imagine if I were to have like an infinite like area of a bathroom and have these tiles of these weird shapes
Yes,
and I
yes,
want to
yes.
put them all over the bathroom floor. It's not clear whether I can cover the entire bathroom floor with these
Basically,
tiles.
yeah, basically.
Yeah.
But of course, this is the particular bathroom. You can say, oh, if the bathroom, like if your bathroom is not that large, you can literally just try it. I mean, of course, you can mathematically compute it, right? The
Yeah.
the, the question is if the bathroom is infinitely large, then of course the computer will take forever, so you can't do
Yeah.
that, right? It says that if it's infinitely large, there's no way for you to just decide, like, hey, can this be done? Okay, and apparently the physicists and the mathematical physicists, they discover that this this decision whether it can be tiled or not is linked to the fact that of the fact that these electrons in these sort of material, whether they have a mass gap or not, right? So it turns out that if you really have a material like that, it's undecidable whether it has such and such property.
Gotcha, gotcha. I think one thing, so I think another problem where this arises, maybe in a slightly different context, you and I were talking about this a little bit back, is how do you know that like the inside of a black hole like exists? You can't actually observe it. And so you can't actually, unless someone goes inside, you can't do it. So in that sense, like, isn't physics incomplete because you can't go inside of it, even if you had observations from the outside and everything was measurable and whatnot, and you
Yeah,
could like reconstruct everything on the surface of a black hole perfectly, given enough time.
yeah. Of course, we don't have full knowledge of the mathematics behind black holes and whatnot, and it's a fair question to ask. You know, like similar to the vein on this infinitely large material, and you can ask the same question about black holes. Like, is the structure of the black hole also undecidable, or maybe you can't figure it out? I would say, I mean, of course, we don't know the answer.
Mhm.
Personally, I would say my hunch is that no, I don't think we should give up just yet. And the reason is this: like when you're given these contrived example on you can't decide whether there's a mass gap or not, it seems like it's contingent on the fact that the system is infinite, right? It's like the
Mhm.
bathroom example, right? Oh, you can't, if you have an infinite bathroom, of course you can't tile infinitely. You can never find out. But if your bathroom has a particular fixed size, you could just go try it out. And in my opinion, every time you have a realistic system, nothing is ever infinite. And
Yep.
and because science, and in particular physics, is a practical discipline, there's this general law that the only thing that's physical is what's observable. And when you observe
Mhm.
something, it's gotta be finite, right? You can't just observe infinity. Like if I get a speedometer and it's like, oh, it's infinite speed, that's probably an error on the speedometer, right?
Yeah.
So so I would say if you discover theoretically or even practically some numbers don't make sense, I feel like that's your fault. I think nature will
Mhm.
always yield some sensible results because it's physics. So I think personally, because of this bit of practicality, I don't
Mhm.
think physics is incomplete.
Huh. I would actually oppose that. Give you an opposing argument. So let me delve into the social scientific realm of things. So in cases where you have markets, financial markets, you can observe, who's buying, like not who's buying and selling, but what the price of a given asset is at a given instant in time. That's observable. You have people who are confined to the laws of physics, and they're these complex organisms with all these neurons and all, you have your body, which is made of basically physical material, and they're making these decisions that are observable in the sense that you can observe what the state of the market is given everybody in it. Yet I'm very skeptical that you'll be able to come up with a model that'll be able to predict such things because there's so much variation. And I'm wondering, like, how would you sort of reconcile that you have, I guess, like, I'm more of the side that certain things are not computable, in general. Like, I don't even know if consciousness is computable, actually. Like, can you determine based
Yeah,
on the laws of physics how a single person is going to act,
yeah,
even if their actions are observable?
yeah, I would say, I guess this is a question of, do you consider what's in principle possible or what's practically possible? And let me just add this. Yeah, so what you're saying is sort of like this. The system is so complex, right? And it's not really feasible to keep track
Mm.
of every individual interactions. Even
Yeah.
though in principle they are real. Like if you really go into it, they are real. So in that sense, if it's just not possible, like let's say even in principle, you cannot create a computer powerful enough to discover those nuances and measure all those things. Like you're saying, does it even make sense that those things exist in a complete way in some sense, right? Like, does it even make sense to model them? So I
Well,
get, yeah,
okay. I was saying modeling is one thing, but I'm actually discussing it more in principle because pragmatically, I don't think you can do it. There's like my understanding of physics is that you pick a particular phenomenon or particular range of validity that you're interested in modeling, and you model that. Like you look at all these different condensed matter material science models, they're not like based on anything like in reality per se. Like some models assume electrons are hopping
yes,
from one
yes,
site to the next. I don't believe electrons are actually hopping. It just happens that this output of this model represents like things that you observe. So you give this interpretation of it hopping around. But similarly, I'm talking more in like in principle that I think there's certain things that are just not computable because of the restrictions of mathematics itself. And mathematics is constrained to represent things that are quantifiable. And I don't know if that can describe like everything. Like describes it's sort of our like closest approximation to objectivity, but it's not truly objective yet.
right. I suppose I see your point, and some of it I can agree with. So, for example, you mentioned that physics, it's you pick a particular field of physics, we use model to approximate reality, and that is indeed true. And on that level, physics is incomplete. It really is, because no matter how hard we try to use our model to approximate real life, it's never going to be 100%, right?
Mm,
And but then here's the next point. You're saying that what if there are stuff about physics that is just not amenable to even the laws of mathematics to predict, right? Then in that
yeah.
sense, maybe it's even more incomplete. Not just in the ways that our approximations are not perfect, but that you can you can just never get there because you don't have the right tools. So so I think to some extent, certainly it feels like in physics some of that seems to be true. It's like quantum physics, right? It's like you
Hmm.
can argue what is quantum fluctuations. It's not observed, but it's like you can interpret it that way. But is it? But I think my perspective is that maybe these things are just not part of physics. Like the unobservable, I guess you can argue that they're part of reality, but if you really truly cannot observe it properly. Oh, okay, there are two parts, right? So the thing is, the the things that you mention are, oh, okay, so you're mentioning there might be some hidden stuff. Let's call this stuff S, hidden stuff,
Sure.
that cannot be modeled by mathematics. Okay,
Yeah.
so there are two possibilities. A, this stuff, can it be measured? Okay, or
Yeah.
can it not be measured? Okay, I would argue that if it cannot be measured, then that's not physics. Because if you cannot measure something, like, why is that physics? And if it can be measured, I would say historically, it seems like we have been able to quantify them in some ways.
Yeah, I thought everything that you can measure, you could quantify. Otherwise, like, how else do you describe it in the language of physics?
Yeah, to some extent, yeah. When you can quantify it, in some sense, it has to interact with some known system that we know, understand, such that it provides some digestible value, like some digits on a screen, right? So, so if there's something that's truly not like modelable by math, it will just give nonsense. Maybe we wouldn't even notice it. It's just like ghosts. It's like, okay.
Oh boy, I think we'll I don't think I would just talk about ghosts at the moment. That's separate discussion. So we have an audience question. Is there something there slash real if we can't observe slash measure it? My answer to that would be I would say maybe a person's subjective experience. It's a little bit, I think it depends on the kind of philosophy that you take, because some people have the philosophy that I don't necessarily agree with this, but the philosophy that like everything is consciousness, like there's no actual physical stuff. It's just like everything is based on your conscious experience. Like your brain is taking these signals and interpreting things, and then there are more physicalists who believe there's actual physical stuff. But minus that, I would just say like a person's subjective experience of a particular event. Like an event can happen, and you can get completely different interpretations based on person's biases, which I don't think can be fully measurable. So that would be my answer to that. What would you say, Tim?
Yeah, I would say I would repeat this law in physics that if something cannot truly be observed or measured, then one could argue that it's really not part of physics. And in fact, we've had in quantum physics that led to breakthroughs, right? It's like if you insist on asking some questions, like, oh yeah, what is the state of a quantum system? Then you're led to kind of nonsense, right? And we try not to do that. So, but of course, there's the other side of the coin, right? Of course, for example, if you believe in this multiverse idea that there are multiple universes, you can also argue that, hey, like, because Einstein's theory says you can't travel faster than the speed of light, so you can never see these multiverse, right? And then you can ask the question, well, do these multiverse exist? But then it's like, well, if you cannot see it, what's the point of talking about multiverse? So I think physics is pragmatic. I think the truth lies somewhere in between. I tend to think that if you truly cannot in principle measure it, then it does not exist. But it's a
Huh.
little less strict than that. Like multiverse, I think you can talk about it, but I don't know. I think it exists more than it's more real than like talking about the state of a quantum system, like the actual quantum state.
Yeah, I think that's that's a good boundary to place of this is what we're considering to be in the realm of physics. I kind of wonder. I guess like we had talked about this a while back when Mikey was here, but the notion of like newer physics coming out and newer mathematics, newer ways of measuring things. Do you think that would be a way of things being like a newer way to quantify things per se?
Oh, you mean as like technology advances, maybe some of, or our understanding of physics advances, maybe some of the things that we didn't used to think were observable become observable, something like that?
Yeah, or rather like more philosophically, if they're because I remember reading a while back different measures of uncertainty. There's like one is probability, which is the most commonly used, and then there's like different kinds of plausibility measures. And I wonder like extending the notion of like what what we sort of like can measure describe quantitatively at like a philosophical level.
Yeah, so
That
yeah.
that might be way too abstract.
Yeah, I think that's a little bit too abstract. I think
Fair,
I, to
fair.
some extent, I think it depends on who you talk to, right? Like someone who's more theoretically inclined might have a different answer than someone who's more like me. My training is in what we call phenomenology, and always the principle is that you always try to measure what you predict, basically. So yeah, I'm
Yeah.
not sure how to answer that.
Yeah, I think like incompleteness goes beyond because I think there's a sort of there's I think two forms of uncertainty. One is where you do some kind of experiment, but there'll be like these random variations that you can't really explain, and you hope they kind of statistically average each other out, and you can quantify that statistically. But then there'll be other things that you can't even quantify the uncertainty of, like there's no statistical way of actually describing it. Like it goes beyond that, I would say. Um,
Yeah, I think the pragmatically our assumption is that we're hopeful, basically. So this goes back to some of the basic assumptions of physics, right? We always assume there's a reasonably consistent external world, right?
mhm,
And in fact, if you look at some of these theoretical models, you can easily cook up things like, uh, let's say the mass of the Higgs boson. Like, what if it's changing? Maybe it's changing so slowly, right? And then maybe in fact maybe it's changing erratically, like completely erratically in some ways, and it's still consistent somehow. And what we measure today, maybe it's completely meaningless. It's completely unpredictable, like 3 years later. I mean, of course, we don't know that. We're not like trying to find the Higgs boson. I mean, all the time, right? I mean, to some extent, we're always
mhm.
taking some sort of average, right?
Yeah.
So, so you can ask the question, like what the heck? Does that even make sense to talk about it? But but then some of this is falsifiable. So it's not incomplete, right? You can go and observe it to see if the Higgs boson's mass fit what we expect theoretically within certain errors, right? You can see if it's consistent. But and then historically it's been fruitful. Everything we've tested so far, sort of fits the profile. But of course there's a bias too. Things that don't fit, we're kind of like, well, we don't know how to model it. But
Yeah, I would agree with that. I think one like last point before we wrap up that I wanted to ask you about, or like get your thoughts on is kind of the study of complexity, where usually the way people model it is they have these really simple agents, like simple units in the system, like the game of life or anything that tries to like create artificial life, where you have these units that interact with each other in simple ways, and they give rise to extremely complicated behavior when you get enough of them together. But my sort of thing is, if you take that analogy to like the brain, for instance, um, even though there are certain like, even though it's neurons firing and it's causing certain thought patterns to happen, I wonder if like that itself, that description itself, would be complete, or if it would have some level of inconsistency to it. Like if you look at complexity itself,
yeah,
in principle.
I think this is a little more subtle because it goes into the idea of computability. It's like
Mm,
sure, I can write down a model that captures every little interactions between neurons. But
mhm.
does that do anything for me? Like, can I use that to compute anything? And I guess if you take the pragmatic approach, maybe the answer is not. At least not so far.
Mhm.
But of course, then you can say, hey, maybe it's just a technological limitation. Maybe you wait long enough, you have a good enough simulation coming along that's able to compute these things. In fact, historically, we have things like this. Like quantum field theory originally was thought so complicated you could not really compute very much. But it turns
Mhm.
out that we have some advances in the lattice field theory. You can use computer to actually kind of simulate some of that. So you can ask the question like maybe maybe in the future we can do more of that, and the same thing goes for this complex system like nuance firing. Like maybe we're just some steps away. So I would say yeah, definitely I mean, to some extent even in the field of physics we're appreciating complex system more.
Hmm.
We're becoming less reductionist, but at the same time, I I don't think we should totally give up. Obviously, right? It's still
Yeah.
worthwhile to look at things in a fundamental way. You know,
Hmm.
and sort of, and this can also help us inform what is the best approach to look at these complex systems. To study these emergent phenomenon. So I don't know. It's complicated. Let's put it this way. The thought itself is complex.
Well said. Well said. So I guess let's we're at time basically. So I think it's time for us to start wrapping up. Um, so you explained what incompleteness was. There's certain theorems in mathematics that you may never be able to prove true or false. And comes from self-referential statements like this statement is false, and then that leads to a contradiction. Is there anything else you want to say about incompleteness before we leave our listeners for this week?
Yeah. I would say that this mathematical theorem definitely, philosophically, kind of was quite a bit of a shock to a lot of people in the field. But its impact on physics is still sort of, to be honest, people don't really care. And it's because at the end of the day, physicists are optimistic, practical beings, I guess, largely. Like, if some things are incomplete, oh, what the heck, like, I guess maybe you discover that you wasted time trying to solve particular problems, and it turns out to be incomplete. Well, you've wasted time, but but unless you try, I guess you can't figure that out. So I would say it's like a cautionary tale about logical system. This could indicate certain limits on the way we infer things, but nonetheless, we keep calm and we keep moving on. So
Yeah, I agree with that. I think it for me personally, I actually revel in it because there are no guarantees in life, and this is just one of those things that gives a mathematical justification that you could spend all this time trying to prove a theorem, but it may never be provable. And knowing that, still going through with it, it's like it strengthens one's convictions more.
I guess
So
so. I guess
yeah,
it humbles us.
yes.
Nature nature is more elusive than you think. So
Yeah. So I think that's a good place for us to stop. So I want to thank everybody for joining us, and we'll see you all here next week.
all right, thank you for joining. Bye everyone.
Bye.